From the fuel that's in your car to the very screen you're watching this on, our entire world is shaped by all these chemical reactions. But here's the thing. Most of them wouldn't just happen on their own. Nope, they need a little push from this hidden, really powerful force. So today, we're going to pull back the curtain on the unseen engine that drives, well, pretty much all of modern manufacturing. Let's just start with a number. 90%. What do you think that represents? Maybe the efficiency of a power plant, or I don't know, the market share of some tech giant. The real answer is actually something way more fundamental, something that's woven right into the fabric of our industrial society. That's right, over 90% of all manufactured products. I'm talking the fuel in your car, the plastics in your phone, even the medicines that keep us healthy, they all rely on this one process called catalysis. I mean, it is everywhere, touching nearly everything we make. Okay, so let's properly introduce this unsung hero of the chemical world. Catalysis is the engine that really makes modern manufacturing possible. It speeds up reactions, makes processes way more efficient, and, as we'll see, a whole lot cleaner. So what exactly is a catalyst? Well, it's a substance that dramatically, and I mean dramatically, speeds up a chemical reaction. But here's the magic part. It comes out the other side completely unchanged. It helps the reaction along without getting used up, so it's ready to do the exact same job over and over and over again. A really great way to think about it is like a chemical matchmaker. It sees two molecules that need to react, grabs them, brings them together in just the right way to, encourage a connection. And then, once they've formed a brand new product, the catalyst just lets go and is off to find the next couple. But how does this chemical matchmaker actually pull it off? What's the secret? Well, it all comes down to energy. It's all about finding a much, much easier path for the reaction to take. So every chemical reaction needs a certain amount of energy just to get started. You can picture it like a giant hill that molecules have to climb. We call that the activation energy. Now, a catalyst doesn't just push them over the top. No, it does something way smarter. It creates an entirely new path, kind of like digging a tunnel straight through the mountain. This new route has a much, much lower energy hill, which makes the whole journey ridiculously faster and easier. And this whole thing happens in a simple, repeatable cycle. First, the reactants, your molecules, they bind to the catalyst. Second, the catalyst holds them in the perfect position to react and form the product. And finally, the new product just pops off, leaving the catalyst totally free to start the cycle all over again. And it can do this millions, sometimes billions of times. Okay, so we know a catalyst lowers the energy hill. But what's actually happening at the very peak? What does that top of the mountain even represent in the real world? Right. That peak isn't just some abstract point on a graph. It represents a real, physical, though incredibly brief, moment in time. That peak is something called the transition state. It's this super unstable, high-energy arrangement where old chemical bonds are breaking and new ones are just starting to form. Molecules only exist like this for a fraction of a second. And the absolute genius of a catalyst is that it's designed to grab onto and stabilize that exact fleeting moment. By making the transition state more stable, it lowers its energy, which in turn lowers the entire hill. And this really shows how our understanding evolved. For decades, early laws just told us that an energy barrier existed. They knew it was there, but not why. Then transition state theory came along and finally explained the why. It gave scientists a map of the journey over the peak, and that was the key to figuring out how to control it. Now, as you can probably imagine, this whole chemical matchmaking business is not a one-size-fits-all kind of deal. Different reactions need very different kinds of catalysts. Broadly speaking, they fall into three main buckets. You've got heterogeneous, where the catalyst is in a different physical state, like a solid catalyst working on gases. These are the absolute workhorses, making up about 80% of all industrial catalysts. Then there's homogeneous, where everything is all mixed together in the same phase. And finally, you have biocatalysis, which uses nature's own little superstars, enzymes. If you look at the two main industrial types, heterogeneous and homogeneous, you can see some really clear trade-offs. Heterogeneous catalysts are generally cheap and super easy to separate out from the final product. That makes them perfect for making massive quantities of stuff like plastics or fuel. Homogeneous catalysts, on the other hand, they're harder to get back, but they're often way faster and way more precise, making them ideal for creating complex, high-value things like pharmaceuticals. And that word, selectivity, it's absolutely key. I mean, check this out. You take one simple molecule, ethanol. With one type of catalyst, the reaction churns out one set of products. But if you use a different catalyst, that exact same ethanol molecule produces something totally different. This shows that the catalyst isn't just a gas pedal, it's a steering wheel. It directs the reaction to the exact destination you want. That's really the heart of it. Same starting line, different guide, different destination. And that level of control, being able to choose the destination of a chemical journey, well, that power has massive implications for our planet. Right, so this power of control and efficiency has a huge modern implication. It's helping us make the entire chemical industry more sustainable. One way we measure this is with something called the E factor, and it's brutally simple. How many kilograms of waste do you make for every single kilogram of the product you actually want? The goal, obviously, is to get that number as close to zero as humanly possible. And when we look at the numbers, wow, the challenge is staggering. Oil refining is incredibly efficient. It produces almost no waste. But then you look at pharmaceuticals. Their complex processes can generate over 100 kilograms of waste for every 1 kilogram of medicine. That is a massive environmental problem, and it's exactly the kind of problem catalysis is perfectly suited to solve. Let's take the process for making a key ingredient in antifreeze. The old method was just messy. It used chlorine, produced enormous amounts of salt waste that got dumped. The new, catalytic way, though, it's so much more elegant. It uses a silver catalyst to combine the starting materials directly with oxygen, and the only major byproduct? Water. Just water. It's cleaner, simpler, and way, way less wasteful. And here's another way to look at it: atom efficiency. It basically asks how many of the atoms you start with actually end up in your final product. For making this one chemical, acetophenone, the old route was only 42% efficient. The new catalytic route, 87%. That's more than twice as efficient, turning your starting materials into the thing you want instead of just waste. And this really gets to the core promise of what we call green chemistry. Catalyst is what transforms the industry, moving it away from just making things and towards a future where we're making things with almost nothing left over. Which leaves us with a final, really inspiring question. We've already used catalysts to do what seemed impossible, like pulling nitrogen from thin air to make fertilizer. So if a catalyst is really just a guide showing molecules a better path, what other paths are just waiting to be discovered? What transformations that seem like science fiction today, like turning waste plastic back into fuel or pulling CO2 directly from the air to make new materials, are just one breakthrough catalyst away from changing our world all over again?